put it in the pore. Finally, what I'll do is, I've counted 1000 points, and if 200 of them are pores, I'll say my porosity is 20%. And if I have had 1000 points and there were 500 of those points were in the paste, I'll say my paste is 50%. And if I had 400 or 300 aggregates, I'll say my aggregate is 30%. So use that as point counting method. Still a very popular method. If you can do enough number of points, you will get good results. And if you make a software do all of this, which your ImageJ can do, even better, right? You don't have to sit and count. I don't think ImageJ does it, but there are other softwares that will do it. You can do point counting. Point counting is still a good method. This is based on something called a one-point correlation function. So I'll tell you the theory. It's a very interesting theory. This point counting thing is, so think about an image and a big image sitting there. And I want to find out what is the fraction of, or say for example, that image has an elephant in it. And how much area of the image has the elephant taken? Right? That's what we are trying to find out. So, do you guys throw this arrow game? What is it called? Dart game, right? You throw this dart and you try to hit the bullseye in the dart. So, assume that you have this dart game and you are a very poor dart thrower. Okay? So, basically I throw the dart. And I throw this image, I throw about 1000 darts. And because I am a very random dart thrower, and you have to be a random dart thrower, you can't get a very professional dart thrower to do this because he'll mess it up. You have to be very bad at doing it, so that you just throw it. So you throw a large number of random darts at this image, and finally, okay, I've thrown 1000, how many have stuck in the elephant? 400 in the elephant, 600 out of the elephant. The elephant occupies 40% of the image area, right? You do it enough number of times and statistically average it, don't you think you will get a right answer? That's why it's as simple as that. So it's a very smart method. Instead of throwing darts, you just say count points. So that is called one-point correlation. Basically, you're correlating with just one point because when you throw a dart, it's a point. It's called a one-point correlation function. There is math behind it also. So this is what it is. Objects that lie partially tested should be counted. So that's why I said if I have something that's lying in between paste and the aggregate, I will give it either paste or aggregate, but the rule of thumb is that if you consider one of them to be the paste, the next one that lies in the paste void interface should be counted as a void. That's what I'm saying. 0.5 chance. One should be, if you count one as paste, the other should be void if it's in the boundary. Again, so think about how much thinking you have to go through. Oh, did I do paste or aggregate the last time? Who is going to remember, right? So you randomly press, you make a lot of mistakes. So that's why software will help you. Volume fraction. So the French geologist Delisle said in 1848. So again, don't think that somebody created this last year. Okay, it's been there for 270 years. We do this enough number of times, my area fraction of voids will be equal to the volume fraction of voids, which means you can realistically upscale from 2D to 3D if you have enough number of images. Basically, your software helps that also now. You tell the software to calculate all these images instead of doing one. And then you go for lunch. By the time you come back, it would have done the calculations. Which means from 2D to 3D, it becomes a very useful tool. Again, what I want to tell you is, if you have nice plain polished images taken from different parts of a sample, 10, 20, 30, 40 of them, you can use that as a quantification tool. Right, I said SEM cannot be used as a quantification tool with just one image, but with enough images, you can be used as a quantification tool. SEM is an identification tool with one image. With multiple images, you can bring your SEM to be a quantification tool. Okay? Okay, I think we can have the air conditioned lower now. I think I'm getting cold. Sorry to trouble you back and forth. Is there a setting that you can put it at a slightly higher temperature so that it'll stay on? Because I'm standing right underneath, it's very cold here. I'll skip this. This is just the mathematics of it. So if any of you want to do the total calculations, length in 3D, length in 2D, it involves some integration. So if you can happily go back to your math classes. Again, why did they teach you integration, right? They taught it for a purpose. They just didn't tell you because they wanted to be a suspense. We can all use all of that. Mean intercept length in 3 dimensions. Again, very important, mean intercept length. So for example, a lot of times you want to look at the distance between particles or distance between, for example, if you have 2 large voids. Distance between the voids, because if I apply a load, the voids will get connected and that will be a point of weakness. So I want the voids to be distributed as uniformly, so I would like to see how far my voids are distributed in the specimen. Now you put in some special material that you want to react in some fashion and you want them to be dispersed all through your concrete. You want to know what is the distribution of that also. Again, simple mathematical calculations to find out spacing between those points, nearest neighbor distances. Very important, right? If I have a cement particle and a limestone particle in the system, if my limestone has to act as a nucleation site for the cement, the limestone cannot be far away from the cement, right? The limestone has to be close to cement, pretty much touching the cement if it has to be a nucleation site. So nearest neighbor distances will become very important. And what is the other advantage of it? You will know what fineness of limestone you would need to make sure that your nearest neighbor distances are small. Right? Now you can start to really engineer your system. Rather than telling somebody, I just randomly put in 15% of limestone, you can tell that I put in 15% of limestone because 15% of limestone gave me a nearest neighbor distance of 100 microns, which was the right distance for me for the nucleation to happen. You see how it starts connecting to the chemistry? Right? You see the link to the chemistry now? Where you can start designing materials. And that is what we should also think of. Designing materials. Now, have you ever heard of a computer manufacturer, a computer chip manufacturer saying, yeah, I randomly put in say 20% silicon, 15% molybdenum, 10% thing, and this thing randomly popped up? No? Right? Have you seen an electronics manufacturer? Have you seen a satellite radio telecommunication manufacturer? Any of these people randomly doing mixed design like we do for concrete? Why? They need so much of controlled properties. Their materials are so expensive. They do it at very controlled scales. That's called materials by design. Concrete is a material by accident. For most of us, still, it's a material by accident. Because somebody tells you, you mix cement, sand, water and aggregates, you will get a hard mass and let's call it concrete. That's what we do. That's what many of us do. So we are still not designing the material because there is no incentive to design. This thing is anyway selling so cheap, why should I waste my time designing, right? But then you see law in terms of the bulk infrastructure. This building, I was walking outside, I was standing outside having breakfast, I was looking at it. It was raining heavily. You see this building? Water is flowing through the sides of the walls completely. In Mangalore, would you design such a building? Should you design such a building? The guest house I'm staying has no eaves on it. It's just flat like this, like a box. So water falls right through the walls. Your concrete is not that forgiving if you make it like this to stand for 50 years. You will have the paint peeling off, you will have water going inside, you will have the steel corroding, and then you cannot complain that my concrete is bad, right? Unless you design. So basically, I want to tell anybody who has designed the structure that if you want this concrete to survive 50 years, you should design it like you should design an underwater structure. That's exactly what that is. Which means your water cement ratio should not be more than 0.35. How many of you think there's a 0.35? How many of you think there's a 0.5 water cement ratio concrete around here? No, right? So it will corrode. Yeah, concrete was very good. I didn't see any holes. Your eyes are not good enough to see 10 microns. And water is only 1.8 angstrom. 10 micron is like a family of water molecules to go through. Right? It doesn't need that much. So people always say, very smooth finish, very dense concrete. How did you know? I looked at it. Oh, you must have X-ray eyes to see that. No. It might have looked good. Of course, if I polish anything and paint it, it will look good. But that doesn't mean it will work well, right? That's where we have to make sure that the perceptions and many times the design and the guest house that I'm in, I couldn't walk down the stairway today from the top to the bottom because it was full of water. Is the staircase inside a building supposed to be dumped with water when it rains outside? It's not the problem of the material, right? It's the problem of the design. And will the designer ever be blamed if this concrete starts corroding and it starts cracking? Will the designer be blamed? Would anybody blame the designer? No. Who should be blamed first? Designer. You should find out, why did you design a building? This is a wonderful building for Rajasthan. Or this is a wonderful building for even Delhi. If you put it on in the Arabian coast, you're asking for trouble. If you put it in Kerala and Mangalore and Bombay. So I was in Bombay, IIT Bombay, Victor Menendez Convention Center, this beautiful new building. We were sitting on the lecture hall 2 years ago. The building was built only a year and a half ago. The false ceiling started to leak. It was raining heavily. The false ceiling started to leak. It started raining heavily in December. False ceiling started to leak. Should the roof of a building leak with concrete? And then they have truss and stuff on top now everywhere, right? So again, functionality, the design. So some of the things that we have to be very cognizant of. I mean, we can sit and talk about microstructure and talk about X-rays and talk about image analysis, talk about cement chemistry, talk about hydration till chickens come home. It's not going to make a difference until collectively we emphasize the fact that a structure is an organic thing. It is not this heap of concrete and wood and steel. It's an organic thing that has to be designed like it's a living being. It's an organic thing with a combination of all these different things. Like we have our skin and muscle and bone and hair and all of that. The building also has all these components that does different things, right? You have to think of it organically and design it such that, I mean, simple example, right? If you lose hair very young and you want to have hair, and some of us lose hair very fast. If you want hair, you will go and transplant. We have techniques now to transplant hair. Why? Because hair does a function. You might not know, but I lived in a very cold place. I lived in a very cold place where temperatures goes to minus 25 degrees Celsius for about a month. The high temperature is about minus 20 degrees Celsius. You know the importance of hair in your head because the maximum heat loss from the body is through the head. You want your hair in the head to keep the heat in your body heat down. Right? There's a function for hair. There's a function for that. We should have buildings designed so that every part should have the functions taken care of. And that's, so otherwise, if we don't look at it, again, I can talk here about concrete microstructure and I can just hold on to it for dear life. But concrete microstructure will make absolutely no sense. I can analyze, I can interpret, I can use a very expensive tool to find out. But if the concrete has a 50% porosity, then it's just an academic exercise to find out what's in the microstructure, right? I might as well bring a big bulldozer, demolish it and build new. That is probably the tool I would need. Not all this sophisticated stuff, right? So get the context, right? Get the idea that all that we are looking at is a collective thing, and it appears in different sizes. If you look at the microstructure, like I said, cement and limestone, their interaction happens at certain scale. If you scale them higher and higher and higher, the beam and column, their interaction happens at a different scale, right? You talk about interatomic forces. I'll give you a simple example quickly just to make that point. Interatomic forces. When two atoms come together, what is the force that they exert between themselves? The nucleus of one is attracting the electron cloud of the other. When they come really, really, really close, the nuclei says we are too close, we should repel, right? So basically it's electrostatic force, weak force. Those are the weak forces. A lot of those weak forces. So what kind of electrostatic forces do you have? Attraction, repulsion. Atoms don't talk of compression and tension and flexion, right? The only natural forces, you talk about a flexural force between sun and moon. Do you talk about a compressive strength between moon and earth? No. What do you talk about? Attraction, repulsion, right? The attractive force and repulsive force in nature. Nature has none of these. We added all these afterwards. So these atoms have these attractive and repulsive forces. When you put the right kind of atoms and molecules together, you can harmonize those forces to what you want, right? You build enough of bonding between those things. You bring these things close together to have a bonding. They bond well. Now when they bond well, they can resist an external force, right? And in concrete, you bond them well to resist the external force called compression. But suddenly, oh, I can't take tension. So you figured out what is the guy who can take tension. Steel came and said, I can do it. So you put steel. Do you put steel everywhere in concrete? No, you wouldn't. You would put only where there are tensile stresses. If you have a beam, you have something called a neutral axis. You put steel only above or below the neutral axis where there is tension, depending on whether it's a cantilever or a simply supported beam, right? So synergy of materials. You see that synergy coming in? At every scale, there is a synergy. And your materials by design should be maximizing the synergy. So, for example, if in a company, different people are working. Somebody is really good in marketing, can sell any damn thing you give him. Somebody is really good in manufacturing and making things. Somebody is very good in computer design of that. Would they normally put these people to the right job so that they harmonize and get it done? Right? Again, in concrete also, it is that harmony that's happening. Fly ash says, I'm a waste material, people are dumping me, put me in concrete, I can give you some silica and alumina free. Concrete says, perfect, fine. Cement says, okay, fine. You can save some cement, fly ash can come in. That synergy comes in. You put in some limestone. Limestone come in and say, okay, I'm really finer. When you grind me with clinker, I'll get really finer, which means calcium hydroxide can lean on me when it forms. You can form faster. I'll give you a lot of surface area. Right? You have another synergy. When synergies start to get disturbed, that's when problems start. Corrosion is a classic example of disturbance of synergy. You remember the passive layer around steel that you want to have? That a layer which is stable at high pH. The moment pH drops, that layer breaks. The synergy is on as long as the pH is high. When a chloride ion comes in or when moisture comes in and breaks the pH, breaks the synergy, that pH goes down, that layer starts to break, and then corrosion is very, very fast. So when you talk about corrosion, you always talk about an initiation time and a propagation time. In life cycle analysis, do you ever consider the propagation time? It's only the initiation time. You break the synergy, you assume that now this is going to go downhill from here only. There is no going back, right? Every material, and that's why, so design of materials. A lot of you are working on recycled aggregate concrete, right? Why do we put recycled aggregates in concrete? From a sustainability point of view, I want to put recycled aggregates in concrete because I don't know where to demolish and put them, right? So I want to use them back in concrete. Great. Sustainability right now, tick. What happens 10 years down the line? I got this demolished concrete from a concrete that was subjected to extreme sulfate attack. Right? My sustainability box was ticked today. 10 years down the line, demolish the structure and built new. Who looks at the sustainability tick mark at that time? Right? Your material was not designed. Your material was, you just used the material just because it was convenient at that time. Lot of people will talk about local materials. Very good-hearted idea of using local materials. But you should also think about the implications of using it and the implications of how long my structure is going to last. If I have to get a material from 50 kilometers away and pay a few rupees extra upfront rather than getting something local and the whole thing failing in 5 years, right? You can afford to do that because at the end of the day, sustainability is a holistic thing. Sustainability is not something that you think of immediately. Sustainability has to be thought of holistically. Sustainability is a larger concept. Again, like I said yesterday, anytime you do concrete, you will have, I'm sure you would have a lot of people who are not working on concrete would have told you, oh, concrete is not a sustainable material, right? Why you use cement? It's not a sustainable material. So we try a very wrong way of justifying. What do you say? No, 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 my concrete is very sustainable because I put in fly ash. Okay, 20% of fly ash, and you suddenly think that by putting a base material, or you say I put recycled aggregate, or I put this and that. That's not the argument. Your argument should be, if concrete is not sustainable, give me an alternate option that can satisfy the functions of this for the time period that this will perform at the cost that this will give you. That is sustainability. Come up with a